Welcome to our executive session on industrial boiler and furnace evolution. My name is Santosh Raikar, and today we're going to explore why a boiler conversion is not just a parts replacement, but a complete re-engineering of the combustion system. We will look at technical evolution, performance, and real-world cases from the pulp and paper industry to guide your future capital decisions. Before we dive into hardware, we must recognize that you have 5 distinct strategic choices for any aging asset. You can keep and restore it, retrofit specific components, convert the fuel and combustion regime, replace the unit entirely, or hybridize it with newer technologies like electric boilers. The goal is to choose the path with the lowest life cycle risk, not just the one with the smallest equipment list. In this first chapter, we move from the concept of a simple furnace to the steam island. We will trace how technology has evolved to solve the shifting constraints of pressure, capacity, and increasingly, environmental emissions. Clear terminology is the foundation of good decisions. It's important to distinguish between the furnace, which is just the volume where heat is released, the boiler or pressure parts, and the boiler island. For conversion projects, the island is our practical boundary because a new fuel affects everything from fuel handling to ash disposal. At its heart, every design is an energy balance governed by physics. Fuel energy enters, and it must exit either as useful steam or as a measurable loss through the stack, moisture, or radiation. When comparing performance, we must always be clear about our measurement boundaries and whether we are using higher or lower heating values. Industrial steam generation has evolved through distinct eras. We started with simple fire tube boilers in the 1800s, moved to high-pressure water tubes, then to pulverized fuel and fluidized beds. Today, we are in the era of the hybrid island. It's important to remember that evolution is driven by specific constraints. The newest technology isn't always the best fit for your specific mill. Why did water tube architecture become the standard for large industrial duty? It's a matter of geometry and safety. By keeping the high-pressure fluid inside small diameter tubes, we can build much larger furnaces and operate at higher pressures. However, this shift makes us far more dependent on precise water chemistry and internal circulation. Circulation is the invisible system that keeps your boiler alive. Whether it's natural circulation driven by density differences or assisted by pumps, the tube metal only survives if the internal cooling is adequate. Modifications during a conversion can disrupt this balance, so it must be carefully modeled. Combustion is governed by the 3 T's: temperature, time, and turbulence, plus the right amount of oxygen. When you change a fuel, you change how it ignites and burns out. This means we have to reprove that the furnace has enough volume and the right mixing patterns to complete the reaction without damaging the equipment. Don't just look at the flame, follow the entire gas path. A conversion redistributes heat. What worked for coal might cause slagging in the furnace with biomass, or corrosion in the air heater due to different acid dew points. Every section of the boiler is interconnected. This checklist represents the true boundary of a conversion. If you change the fuel but forget to evaluate the ash transport or the control logic, the project will fail. We have to ask, what happens if we miss this? At every stage, from fuel receipt to the final emission stack. Now let's look at the furnace technology portfolio. Different fuels require different methods to introduce, suspend, and mix the fuel to ensure complete combustion. Fire tube and package boilers are the workhorses for smaller loads. They are compact and fast to deploy. However, they have strict pressure limits and a large volume of stored water, which makes them sensitive to thermal stress and harder to convert to solid fuels. Within water tube package boilers, you'll often hear about D-, and O types. These letters simply describe the physical arrangement of the drums and tubes. While they offer different footprints, the selection is usually driven by shipping limits rather than a difference in performance grade. Grate and stoker firing is a rugged, time-tested technology for solid fuels like bark and wood. The fuel burns in a bed, but the real challenge is managing fuel moisture swings and ensuring that the overfire air is mixing well enough to prevent high CO emissions. Pulverized coal firing involves grinding fuel into a fine dust to burn it in suspension. It allows for massive capacity and rapid response, but but it brings hazards like coal, dust explosions, and complex slagging issues. Converting these to gas often changes the radiant heat profile significantly. Bubbling fluidized beds, BFB, use a hot sand bed to create thermal inertia. This makes them excellent for wet fuels like sludge or biomass. They are very conversion-friendly because they often allow for an open bottom design, but you must be careful about agglomeration where the bed material sticks together. Circulating fluidized beds, CFB, take the BFB concept further by entraining the solids in a high-velocity loop. This provides incredible fuel flexibility and high burnout rates. The trade-off is the mechanical wear from the circulating solids and the complexity of the separator and refractory systems. Heat recovery steam generators, HRSG, are common in combined heat and power plants. They capture the waste energy from a gas turbine. While efficient, they are susceptible to thermal fatigue from frequent cycling and require careful management of the pinch point, where heat transfer is least efficient. Electric boilers are gaining traction as we decarbonize. They have no on-site emissions and can ramp up very quickly. Here, the constraints aren't combustion-related. Instead, you have to worry about grid capacity, demand charges, and extremely high water conductivity requirements. Sometimes, direct firing isn't the best fit. Gasification allows us to turn difficult solid residues into a clean-burning gas first. This can protect your main boiler from contaminants, but it adds significant complexity in terms of tar management and gas cleanup. Now, let's get into the technical details. Our technical atlas will examine how fuel admission, bed motion, and chemistry define different furnace families. We can classify furnaces by how the solids behave, from stationary grates to fluidized beds and chemical recovery units. Each hardware family is designed to handle a specific type of residue and combustion regime. Fixed, shaker, and underfeed grates are simple but limited. They work best with predictable, dry fuels. If the fuel varies, you often run into clinkering or air channeling because the bed isn't being constantly agitated. Traveling and chain grates act like a conveyor belt. The key control variables here are grate speed and bed depth. If you see high carbon in the ash, it's a fingerprint of poor mixing or insufficient residence time on the grate. The difference between mass feed and spreader stokers is where the burning starts. Spreader stokers throw fuel across the furnace, so fines burn in suspension. For any retrofit, you must prove the feeder throw can handle your specific particle size and moisture. Water-cooled vibrating grates level the bed through vibration while protecting the grate surface with boiler water. This allows for higher air temperatures. When engineering these, we focus on the vibration frequency and the integrity of the water-cooled panels. Reciprocating or stepped grates use a walking motion to turn over a thick bed of fuel. This makes them great for difficult materials like bagasse. However, the hydraulic systems and side seals require high maintenance to remain reliable. In waste-to-energy applications, roller and moving grates are used to precisely control the residence time in different zones. This ensures that even the most heterogeneous waste is fully combusted and cooled before discharge. The DynaGrate is a specialized shaft step design that creates a longitudinal wave. This exposes new burning surfaces constantly, which is vital for high-efficiency waste-to-energy modules. This selection matrix helps us match the grate to the fuel. If you have high fuel variability and need strong bed agitation, a reciprocating or roller grate is a much better fit than a simple traveling grate. When a grate furnace struggles, don't just add more air. Read the bed first. Look for uneven distribution or leaking seals. Often, the problem isn't the total airflow, but where that air is actually going relative to the fuel. The fluidized bed family is defined by gas velocity. BFBs keep the solids in a bubbling mass at the bottom, while CFBs circulate them through the entire furnace. This choice determines your erosion risks and how you'll manage bed inventory. In suspension firing, we move away from grates and focus on flame aerodynamics. Whether it's wall-fired, tangential, or a cyclone furnace, the control mechanism shifts to fuel preparation and burner staging. For the most difficult hazardous wastes or sludges, a rotary kiln is the standard. It uses a rotating refractory shell to tumble solids. In these systems, the downstream secondary combustion chamber is just as critical as the kiln itself. Multiple hearth furnaces use a vertical stack of hearths to dry and burn solids. While largely replaced by fluidized beds and modern mill sludge projects, they remain an important part of the historical technology landscape. A craft recovery boiler is a unique chemical reactor. It doesn't just burn fuel, it recovers pulping chemicals. Black liquor is sprayed into droplets that dry and burn to form a char bed, eventually melting into a smelt that drains from the bottom. The liquor guns are the heart of a recovery boiler. If the droplets are too fine, they carry over and plug the upper boiler. If they are too coarse, they hit the walls and destabilize the char bed. Controlling viscosity and pressure is non-negotiable. Air systems in recovery boilers are multi-level. Primary air controls the bed edge. Secondary air mixes the lower furnace, and tertiary air completes the burnout. Modern systems often use more than 3 levels to fine-tune emissions like no. The char bed shape is actually a process measurement. A bed that is too high can block air ports, while a cold bed can weaken chemical reduction. We use bed cameras to ensure we have stable smelt drainage and chemical efficiency. When discussing recovery boiler floors, use the correct terminology. A decanting floor means the spouts are elevated, creating a permanent pool of smelt. This design requires specific floor protection and inspection procedures compared to sloped floors. This control card summarizes the critical conditions for decanting floors. From spout restrictions to the ultimate smelt water hazard, the goal is always stability. If you see heavy runoff, follow your site response plan immediately. Never improvise. Drum configuration, whether single or 2-drum, changes how water circulates and how the bank is built. While single drum designs are common for very high-pressure modern units, both must perform the same 3 chemical recovery duties. The industry moved from direct contact evaporators to low-odor designs to reduce sulfur emissions. If you're modifying an older unit, you must rebalance the entire heat recovery train because you no longer have that direct gas-to-liquor interface. Modern designs, like those from Anritz, offer high-energy recovery configurations. They use wider bank spacing and advanced air controls to maximize efficiency while managing the high dust loads inherent in recovery duty. Sulfite recovery is different from craft. The goal is to recover cooking acid value, not produce green liquor. This changes the ash chemistry and requires the boiler to handle integrated streams like methanol or furfural. In a sulfite system, the boiler is just one part of a multi-stage train. You must guarantee the chemical quality of the acid being returned to the process, not just the steam being produced. It's an integrated chemical reactor loop. To summarize, similar-looking pressure parts can house very different chemistry. Whether it's craft, sulfite, or even a Sodex effluent boiler, the downstream interface defines the engineering requirements. In Chapter 3, we move into failure fingerprints. Troubleshooting is about separating the effects of fuel, heat transfer, and measurement to find the root cause of an issue. A fuel specification isn't just a contract, it's an operating manual. Moisture affects net heat, particle size affects carryover, and alkali content predicts how quickly your boiler will corrode or foul. When looking at boiler efficiency, always read the loss stack. A conversion might improve combustion, but increase stack losses. Always declare your test basis, HHV versus LHV, so everyone is looking at the same numbers. Not all deposits are the same. Slagging happens in the hot furnace and is often molten. Fouling happens in the cooler convective passes. Each requires a different mitigation strategy, from fuel blending to soot blower optimization. Corrosion and erosion work on different clocks. Corrosion is chemical, often driven by chlorine or acid dew points. Erosion is mechanical, driven by high gas velocity. You must identify the mechanism before you can select the right repair material. Air leakage is a hidden tax on your capacity. Your fans have a finite capacity. Every kilogram of air leaking in through a door or expansion joint is a kilogram of air that isn't helping you burn fuel. Emissions are the fingerprints of your combustion process. High CO tells you about mixing. High NO tells you about temperature and stoichiometry. Always try to control the formation mechanism before you rely on expensive end-of-pipe cleanup equipment. Even the best combustion system can overcome poor water chemistry. Oxygen control and steam purity are vital to protecting your turbine from deposition and your boiler tubes from internal damage. Scientific diagnosis starts with validating your data. Don't tune a multi-million-dollar asset based on a bad instrument. Reconcile the mass and energy balance first, then test a single hypothesis at a time. Now we move to the how-to of conversion. This ladder starts with defining the service need and ends with sustaining the new performance level. Integration is the key to execution. Every project needs no-go gates. If the fuel supply isn't bankable or the asset's remaining life is too short, the gate should stop or redirect the project. This prevents you from throwing good money after bad. As an owner, your input data pack is critical. If you provide poor operating history or inaccurate as-built geometry, the engineering models will look precise, but will be fundamentally unreliable. Remaining life is a design input, not a footnote. We must ask, can the old pressure boundary carry the new business plan? If the conversion increases cycling or changes metal temperatures, we need a fitness for service review. One design point is never enough. We need to model multiple cases: wet fuel, low load, and maximum continuous rating. This ensures the fans and pumps have enough margin for the bad days. Computational fluid dynamics, or CFD, is a powerful tool, but it's a question, not a decoration. We use it to test hypotheses about air staging and temperature. A pretty color plot only has value if it's calibrated against real plant data. A circulation review is mandatory for any significant change in heat release. We have to ensure that the tubes won't overheat due to departure from nucleate boiling, and that the headers can handle the new thermal expansion paths. Size your gas path for a dirty plant. A data sheet might show plenty of fan margin, but once the air heater is fouled and the casing has minor leaks, that margin disappears. Always designed for the aged, real-world state. In solid fuel conversions, the fuel handling system is your reliability engine. The best furnace in the world will fail if the feed is interrupted by bridging, freezing, or metal contamination. Designed for the worst fuel day, the tail of the conversion is your residue. You need a lawful, reliable plan for every kilogram of ash and every liter of scrubber wastewater. A fuel strategy isn't complete until the waste streams are accounted for. Control and protection systems must match your new fuel. From the purge sequence to the master fuel trip logic, every step must be proven through functional tests. There is no room for improvisation in safety logic. Permitting is often the longest lead item. You need to close the gaps on air permits, pressure codes, and community engagement early. Schedule risk usually starts here, long before the first weld is made. Constructability starts in the design phase. By using laser scans and prefabricating modules, you can significantly shorten the outage. The goal is to move as much work as possible to the pre-outage phase. When you buy a conversion, you're buying outcomes. Your contract should have clear boundaries and guarantees for capacity, efficiency, and emissions, with agreed-upon test methods like ASME PTC4. A typical timeline can span 12 to 24 months. Don't let schedule pressure force you into accepting unresolved risks. The permit strategy and long lead equipment releases must be tied to your decision gates. Outage execution follows a strict sequence: isolate, modify, verify, energize, and finally commission. Mechanical completion is only the halfway point. The plant isn't ready until the controls and safety loops are fully verified. Commissioning should move in expanding envelopes. We start with cold logic checks, move to light off, then low load heat up, and finally to fuel corners, the worst credible fuel cases, before we run the final guarantee test. In Chapter 5, we'll look at public cases to see what lessons we can transfer to your own projects. At Domter Nakusa, 3 boilers were converted from coal/stoker to natural gas. By focusing on prefabrication, they completed the outages ahead of schedule. The lesson here is that even a simple gas conversion requires significant furnace and control engineering. This B&W case study shows how a recovery boiler was repurposed into an open-bottom BFB for residues. They reuse the upper island and back pass, effectively turning chemical recovery geometry into energy service. It's all about thermal compatibility. Domter Kingsport is an example of a total mill transformation. When they switched to recycled containerboard, they redesigned their entire steam island. Boiler projects should always follow the future material balance of the mill. Kohler Oberkirch converted a large CFB from coal to biomass. This was a major capex project that included new feeding systems and emissions controls. It proves that CFB flexibility still requires a bankable biomass supply and robust logistics. SAPI and UPM are leading the way in electrification. By adding e-boilers and steam accumulators, they can respond to grid prices and decarbonize in parallel with traditional combustion. Value comes from flexible dispatch. What transfers from these cases? Reuse can create value, and the fuel always drives the scope. But remember, the condition of your assets and your local fuel contaminants must be re-engineered from scratch. Once you've converted, how do you handle the abnormal? Chapter 6 provides the playbook for troubleshooting after a conversion. In the first 24 hours of a problem, stabilize the plant first. Respect your trips and limits. Preserve the evidence, samples, photos, and alarm logs before you start diagnosing the mechanism. If you have low output but high O2, the furnace is struggling to release heat. Check your fuel moisture and air leakage first. Reconcile the heat balance before you start changing settings blindly. When NO, CO, or opacity rise together, it's a sign that your combustion window has shifted. Check for fuel excursions or fines carryover. Always return to a known stable blend before attempting a retune. For fluidized beds, bed agglomeration is a major risk. If you see a shift in pressure drop or temperature spread, you may have low melting alkalis sticking the sand together. Control the temperature and refresh the bed material immediately. Rising stack temperature usually means fouling. If soot blowing isn't fixing it, you may have changed ash chemistry or have internal bypasses. Re-baseline only after you've verified the cleaning system is working correctly. High tube metal temperatures are a pressure boundary warning. Don't just increase the spray water. Find out why the heat has shifted. It could be flame impingement or internal fouling that's disrupting circulation. Furnace pressure instability often points to a mismatch between the fuel feed and the ID fan. Check for leakage and verify your fan curves. A clean datasheet won't help you if the physical casing is leaking. A successful furnace can still be a failed steam island if the ash or fuel systems keep tripping. Map your single points of failure and ensure you have the right spares. Reliability is about the whole system, not just the fire. Stabilization takes 90 days. You start with daily risk reviews, move to optimizing the modes, and finally standardize the training and KPIs. Commissioning only ends when the performance is repeatable across all shifts. Finally, we look at leadership. Transforming a steam system requires more than just capital. It requires a convergence of fuel strategy, operating discipline, and technical skills. The business case for conversion must include avoided risk. If you only look at CAPEX, you'll miss the value of production continuity and the option value of being able to switch fuels in the future. Price is what you pay. Value is what you protect. Executives should look at a balanced dashboard. Don't just watch cost. Look at leading signals like fuel envelope excursions and protection bypasses. If your integrity backlog is growing, your future reliability is at risk. Every mill needs a steam master plan. Sometimes the best new capacity is the steam you stop wasting. Sequence your projects as a portfolio that balances demand reduction with supply reliability. The emerging hybrid island combines the best of all worlds: biomass for base load, gas for backup, and electric boilers for grid response. This portfolio approach provides the ultimate resilience against shifting fuel and carbon markets. Your 24-month roadmap starts with a baseline. Don't commit irreversible capital until you've screened the fatal flaws and finish your feed studies. And crucially, name one executive sponsor for the whole steam island to avoid siloed decisions. In closing, the commitment is simple. Don't ask an old boiler to carry a new strategy without proving the engineering. The right conversion is an unlock. The wrong one is a legacy of frustration. Choose based on evidence, We've built this session on industry standard sources, from ASME and NFPA to the latest vendor papers. All of these references are available for your technical teams to review in detail. Thank you for your time. Please note the visual credits and the disclaimer. This presentation is for professional education and does not replace qualified site-specific engineering and safety procedures. I'm now open for your questions.